For section 3.4, we are going to take a look at linear programming. And linear programming is a method of finding a maximum or minimum value of a function that satisfies a given set of conditions called constraints. And the constraints are one of the inequalities in a linear programming problem. And for the problems that you're going to get today, there's going to be 4 constraints that we have to graph. The feasible region is the solution to the set of constraints. So there's going to be a shaded region that you end up with once you graph the constraints, and that shaded region is called the feasible region. So it's where all the ordered pairs satisfy all inequalities given. So for example 1 here, we are going to graph this feasible region for the following constraints. So the first one is x is greater than or equal to 0. So on the x-axis, we are going to put a dot at 0. And then, if x equals 0, y can be anything. So we are going to have another point up there somewhere, or we could have put it down farther, anywhere on the y-axis. And our inequality symbol is underlined, so we are going to connect this and make it a straight, solid line. And y is greater, or sorry, x is greater, so we're going to look at this region over here. Then we're going to graph y is greater than or equal to 1.5. So we're going to go to 1.5 on the y-axis. And this time we're talking about the y, so x can be, or our other point can be anywhere across. It's going to make a horizontal line. So then we have to draw this line, and again it's underlined, so it gets a solid line, and I should have done it all in blue. And y is greater than 1.5, so then that is talking about that region up there. And then for our next constraint, we're going to have to solve for y so that we can graph it. So I'm going to minus 2.5x from both sides. So I'm going to have 5y is less than or equal to 20 minus 2.5x. And then we have to divide everything by 5 here. So 20 divided by 5 is 4. And then negative 2.5 over 5 is actually 1/2. 2.5 is half of 5. And then our x. So our y-intercept here is 4. So positive 4. And then our slope is negative 1/2. So down 1 and over 2. And I'm going to do that a couple more times just so I can draw a line where I need to draw it. And again, the inequality symbol is underlined. So this is going to be a solid line. And y is less than this. So this is going to get shaded all underneath here. And then we have one more to do here. And we have to, again, solve for y. So I have 3x plus 2y is less than or equal to 12. I'm going to minus 3x from both sides. So I'm going to have 2y is less than or equal to 12 minus 3x. And then I'm going to divide everything by 2. So that would be a 6, and that would be a negative 3/2 x. So our y-intercept is 6. So a dot at 6. And our slope is negative 3/2, so down 3 and over 2. 1, 2, 1, 2, 3, 2. And we're going to draw our line. Again, it's underlined, so this is going to be a solid line as well. And y is less than this. So then we're going to shade here. So looking at this, we have to figure out where our shading overlaps. So remembering there was a line here, And we're under the pink line and under the purple line and above the blue line. So our feasible region is right here. Now we have an objective function, and that best combination of values in order to minimize or maximize a certain function, which is that objective function. So we're going to talk about that in a little bit here. We have these pictures here of bounded and unbounded regions. A bounded feasible region just means that the region is closed on all sides. And an unbounded region is one that has an open side. As you can see here, this is open down here at the bottom, and this is open here on the top side-ish area. So if an objective function has a maximum or minimum value, it must occur at one or more of the vertices of the feasible region. So once we graph all of this, we really only care about the ordered pairs that are at the vertexes, at the corners of our feasible region. So we really have to take some time and make sure that we graph correctly. So this right here is our same problem that I had you do, or that we just did on the example up above. So if I go back to this graph, we look like we go from 1.5 up to 4 on the y-axis. So instead of going through all of this and graphing, I'm just going to kind of copy it down. So 1.5 up to 4 is going to be their one side. And then it looks like it goes over to 3 1.5, so about there. And then the other one is over 2 up 3. So again, you can copy that graph from above, but this is the same one. This is where our feasible region is. So the ordered pairs that we really care about right here is this one over 0 up 1.5. This one is over 3 up 1.5. This one is over 2 up 3, and then over 0 up 4. So those are the 4 points that we're going to take a look at. And now our objective function they gave us is 25x plus 30y. So what we're going to do is plug in each of these ordered pairs. So the first one is 0, 4. And I'm going to plug in 0 for x and 4 for y. So I'm going to have 25 times 0 plus 30 times 4. So that would be 0 plus 120, which would give us 120 out for an answer. Then I'm going to plug in 0, 1.5. I'm going to have 25 times 0 plus 30 times 1.5. So that would be 0 plus 45, which would give us 45. And then another ordered pair we have is 3, 1.5. So the 30 times 1.5 is going to be 45, and then 25 times 3 is 75. So 75 plus 45 would be 120. And then 2, 3. So 25 times 2 and 30 times 3. So that would be 90 and 50. If we added that together, we would get 140. So they were asking us to maximize. So what we're looking for is the largest answer here. So our maximizing is actually going to be 140, because that's the highest answer that we got. So P equals 140 is how you would write your answer there. One thing I want to point out is this question asked us to maximize. Some of the questions will say minimize. So if it says minimize, they want the smallest answer. So in that case, if that was a minimize the objective function here, we would have picked p equals 45 because we want the smallest number. So make sure you pay attention to that one word in the question.